All right, thanks SUSE for having me at the booth today. I'm representing AMD and I'm in the Radeon Instinct group. So that's the GPU compute for the data center space. I'm the product manager for the software side for GPU compute, focusing on machine learning and HPC. So where do we see our vision of the data center going is the combination of world-class CPU and GPU systems, together with a fully open source software stack based on Linux, very similar to the Linux environments that SUSE provides us, and programming environments that are fully open source and available to download today. We've been working with the ecosystem, and I'll talk a little bit more as we go through the presentation. So what's really driving the HPC side of things is the win with Frontier. This is a nice win with the CPU and GPU and being able to drive the software ecosystem, because there's a lot of applications that need to be able to run performant and portable across many different platforms. From our GPU roadmap, we have the MI25. It's been shipping for the past year or so. People have developed a lot of software with that. MI50 is available today, and MI Next is on track with future hardware roadmap coming with Frontier. So what's available today is MI50. It's the world's first 7 nanometer GPU. It's available in both 32 and 16 gigabyte versions. It's looks like the font's got a little messed up, but it is also the first PCIe Gen 4 GPU. So together with the Rome architecture of the CPU, it has very high bandwidth capable systems to be built. And here are some examples of those systems available or announced at Supercomputing. So a few from Gigabyte and one from Penguin, supporting up to 8 or even 10 GPUs with a switch. These systems are available through the providers, and they really have really high bandwidth and really power efficient. So talking a little bit more about the software, we see OpenMP as one of the main programming environments for the software ecosystem in the exascale space. People are porting their applications to that today, as well as the unified CPU and GPU tools. So this is a way to be able to profile or debug your platform. You need to have those integrated tightly so that you understand where your deficiencies are in your application. In terms of machine learning, we have optimized and upstream versions of Tensorflow and PipeTorch. So those are available today, constant continuous integration being built. So every time someone checks in a change to that code base, it runs regression on those servers. And that's all fully public. Then we're really trying to drive this 100% open source strategy. So last year at Supercomputing, we announced ROCm 2.0, really focused on the machine learning frameworks. We hadn't done a lot of work in the HPC space, and this year with the Supercomputing, we're announcing 3.0. We've spent a lot of time and effort on the libraries to build up support for HPC applications. We've also enabled the ecosystem through Singularity and Slurm, so you can deploy your jobs, package up your applications. With Docker and Kubernetes, it's a little more common in the machine learning space. The debugger we have is based on GDB. It'll be available this fall with nice integrations working into the IDEs. So we're not providing our own IDE, but the system ones that are available on the market today interact with the standard GDB interface. We've also implemented UCX. So OpenMPI and MPitch work on top of UCX to scale out HPC type applications. RICL is equivalent to Nickel in terms of a communication library for machine learning. And then all of these are built on the programming models, either HIP, OpenCL, straight Python, and OpenMP. And so with OpenMP, we have a demonstration over at the booth you can go take a look at. So I mentioned TensorFlow and PipeTorch. Here's just a couple screen grabs of the community builds. So they run nightly, and you can see the status or get the most recent version there. In terms of scaling out, we built a system with 32 GPUs. This is 8 GPUs per system, connected with a Mellanox switch. and it scales almost linearly. So the performance of one GPU to 32 is close to linear. In terms of the compiler, we've built a HIP, is HIP Clang. It's built on the LLVM infrastructure. That's compiles to our AMD GCN backend. The backend is, the ISA is fully public, so you can download it and build it. We've had other companies actually take the ISA, build GCC support. So it's totally doable. With HIP, I'll go into a little more detail of how we can port some of the CUDA applications and how it works there. But I wanted to mention the OpenMP. So today we have 4.5 support and building out the 5.0 for the Pragma offload to GPU targets. In terms of HIP, HIP is a portable C++ interface that allows you to target both the CUDA and the AMD tool chains. So this way your application stays constant at the top level, and you can just change your compiler flags to build for a different environment. It's fully open source. Again, the APIs are very similar to a CUDA type infrastructure, and at the kernel level you can see it's actually identical. So the low layers of the math, there's nothing really changed. It's really the way that HIP is being ported and called. And to make it even easier to translate, we have two tools. It's called Hipify. One's Clang-based, so it's an interface to the LLVM front end, and it's like a preprocessor for the compiler. And Perl is more just a standard replacement script, so it looks for the CUDA type declarations and changes it for HIP. We've worked with NAG to build or port to the CUDA library. So this is the nice tongue twister, CUDA on CUDA. But it has a lot of the complex CUDA code, uses a lot of external libraries, and within 15 days he had the full test infrastructure up and running with the library ported. If you want to know more about HIP porting processes, we're hosting a couple sessions just down the road at the Rock Bottom Brewery. Today's is already over, but there's one tomorrow afternoon and one Thursday morning. So you can contact me if you're interested, and I can get you signed up for that. So as a closing in terms of performance, this is where we want to highlight the benefits of the AMD CPU and GPU solutions. So with an AMD 8 GPU benchmark, we're about 25% faster than the NVIDIA on Intel. So this is a top-end Intel CPU, the dual Xeon with 8 V100s compared to the new Rome processor. So it's a dual-core, dual node EPYC Rome with 8 of the MI50s. And this shows the architecture where there's no switches in place. Here there's a lot of PCI switches. And so with the combination of the CPU load and the GPU load, we get the faster performance and scaling. So in terms of the ecosystem, we've got a device plugin for Docker and a device plugin for Kubernetes, and you can use Docker containers on that. So we have pre-built Docker containers for base development, all the machine learning workloads. We've got a Singularity. It's enabled in their main repository now, and as well as support for Slurm for workload management. Trace Compass we've used for the PAPI interface to the profiler, as well as using Eclipse and some of the other GUI interfaces for the GDB. The whole strategy sort of falls around ECP. So as we go towards the frontier infrastructure, it's scaling out these tools for many, many nodes. So that's how we see the drive for the ecosystem to exascale is delivering open source software together with the top-end hardware and providing a solution for the industry that's portable and performant. So thank you for your time. Any questions?